So we are very happy to have Vedika from Stanford, and she will tell us about the post-selection-free entanglement dynamics via space-time duality.
Yeah, thanks very much to Masamichi, Hugo, Rafael for inviting me. This is a really exciting collaboration and workshop, and I'm very happy to be here. So
Thanks
today
for
I'll
coming.
be, yeah. So today I'll be telling you about this this work that we posted very recently in the archive. This work was really led in by Matteo Ippoliti, who's a postdoc at Stanford. He did all the heavy lifting, and he's here on the call. So if I say something wrong, he'll be here to correct me. Okay, so as people in this collaboration need no introduction to this. Everyone's well aware that this is a really exciting time for many body physics when we're exploring questions that are far outside the traditional regimes, which are focused on kind of equilibrium or near equilibrium properties of time-independent Hamiltonians. Instead, we've been thinking about this much wider class of quantum evolutions, including dynamics from general initial states, which are not low energy in any useful sense, and more general classes of quantum evolutions, for example, unitary evolutions that need not be generated by time-independent Hamiltonians, that may be in the form of quantum circuits. The unitary evolutions may possibly be interrupted by non-unitary measurements for monitoring, readout, control. We're just exploring this much broader class of evolutions. And these general evolutions open up this new continent for studying many body physics, which is increasingly important in the light of rapid development of NISQ devices, right, with these unprecedented control measurement capabilities. And this has created this really exciting opportunity, not just for translating concepts from familiar equilibrium statistical mechanics, such as notions of phases and universality classes, to the out of equilibrium setting, but also for developing completely new paradigms. For instance, using tools of many body physics to think about questions of simulability of quantum evolutions, which gets to questions of complexity, quantum advantage. And a common thread through all of these explorations is really the dynamics of quantum entanglement, which, as we heard in great detail in the last talk, is itself becoming an actual observable in experiments, right? So in this talk, I'm going to focus on one very small aspect of this larger program, which is to study entanglement dynamics. And here there's kind of, as far as I'm aware, there's kind of two really crisp examples where the dynamics of quantum entanglement can show a sharp phase transition, which are invisible to traditional thermodynamic measures, right? So perhaps the most familiar example to everyone is that of many body localization. The many body localization is a phase transition that can take place either in time-independent Hamiltonians or flow case systems. It's not possible in random and time quantum circuits, right? But nevertheless, as some parameters such as the disorder strength is tuned, there is a sharp transition in the dynamics of entanglement in the system. And one signature of this transition is that the entanglement growth can go from being some kind of polynomial in time to logarithmic in time in the MBL phase, right? Another more recent example of an entanglement phase transition in quantum dynamics takes place in this class of unitary projective circuits that I believe you heard about in a recent GeoFlow meeting. So this is a class of circuits that was introduced in Matthew Fisher's group and Adam Nahum's group. And what the scenario they had in mind is that this is a very simple toy model for open system dynamics, right? So you have unitary gates. You're doing time evolution under this circuit. You have unitary gates. These can be random unitaries. They can be unitaries drawn from various ensembles, like the Haar ensemble, Clifford's, whatever you want, right? And then these unitary gates are interrupted by local projective measurements, which take place at some rate. And then you look at the behavior of individual quantum trajectories under this evolution. Okay, so for instance, if you start with some density matrix under this evolution, you're going to unitarily evolve it in the usual way. But then when you do the projective measurement, you want to pick a single trajectory which corresponds to a specific measurement outcome, which is indicated here by alpha. Okay, so we're not going to average over measurement outcomes. And the question was, how does this kind of balance between coherence and decoherence. The unitary evolution is coherent, the measurements are decoherent. And the question is, how does this kind of this balance between coherence and decoherence happen in these systems? And conventional wisdom would have told you that your decoherence always wins. So your states become, when you're looking at these quantum trajectories, they become increasingly disentangled because you're getting entangled with some outside environment, right? So they're losing entanglement between themselves. They're just going towards some disentangling area law phase. But surprisingly, what these papers found is that there's actually a robust volume law entanglement for some rate of measurements that is smaller than some critical measurement rate. Okay, so heuristically, this unitary dynamics, you have this competition between unitary dynamics, which is causing your entanglement to increase, and these measurements, which are causing your entanglement to decrease, and you can actually get this sharp transition. And a very nice intuitive picture for the transition, which was proposed by members of this collaboration, is that you can really think of the unitary dynamics as generating a kind of novel quantum error correcting code, because unitary dynamics is scrambling your quantum information and hiding it in these very global degrees of freedom, so that when your local measurements go in and when you go in and locally measure the system, you're not actually gaining that much information about the system. So you can actually get this late time entangled phase. Okay, so I'm going to focus on this class of this class of models in this talk, right? I'm going to use the word hybrid quantum dynamics to refer to these dynamics where you have a mixture of unitary evolutions and projective measurements. And just as a very quick review, so we can look again at pure state dynamics under these hybrid evolutions. So you can do something like measure the entanglement entropy starting from some initial state subject to this hybrid circuit in time. And in the pure state dynamics, you get two distinct entanglement phases. Okay, so when your measurement rate is less than PC, your steady state is a volume law. When your entanglement rate is greater than PC, so you're making very, very frequent measurements, you're constantly collapsing your state, then you get an area law in time. Okay. But instead of thinking of just pure state dynamics, a very useful perspective on this transition comes from equivalently thinking about mixed state dynamics. Okay, so when you think about mixed state dynamics, these entanglement phases actually end up looking like purification phases. Okay, so you can start with a completely mixed initial state, say the identity, you evolve it under this circuit, and you ask, does the state remain mixed or does it purify? Okay, and again, when your measurements are small enough, then your phase remains mixed. And if for a large enough measurement rate, you end up purifying. Okay. And here I should say that, you do have to think about the time at which you purify, because, if you have a finite system and you wait long enough, you're always going to purify. But the point is that in this mixed phase, or this volume law phase, this purification takes a time that's exponentially long in the system size. But in the pure or critical phases, this time is parametrically smaller. Okay. So that's just the very broad bones introduction that, we have these two phases, we have this phase transition, but actually there's this whole host of very rich questions about both the nature of each of these phases. Okay, so just this volume law phase is not a traditional, thermal phase. It's not at all thermal. So there's lots of interesting features about different correlations in this volume law phase, about the nature of this dynamically generated quantum error correcting code. There's a lot of interesting questions even in the area law phase, because you have these steady states which obey an area law. So you can ask about notions of quantum order phases as diagnosed by these non-trivial steady states. The nature of this transition is also an interesting direction for exploration. What are the universality properties of it? Can you map it to StatMech models? It seems to look like it has a CFT description, but so in general, there's a whole host of questions both on either side of the transition and about the critical point. Okay, so that's the whirlwind introduction, right, to what we'll be talking about. And one thing that I want to connect with here, which ties in nicely with the last talk, is how do we try to even start studying some of this in experiment? Okay, and what are the challenges with studying this in experiment? And the first challenge that you encounter when thinking about monitored dynamics with measurements is the problem of post-selection. Okay, so any protocol that you have for measuring entropy requires you to prepare the same state multiple times. Okay, so for instance, this is the measurement of entanglement entropy from Marcus Greiner's group required you to simultaneously prepare two copies of the same state, right? And then do this operation on it. Whereas the proposal from Peter Zoller's group that we just heard about with randomized measurements, this still requires preparing the same state, but you can do this sequentially. You can do it over and over and over again, right? So in the last talk, we heard that you started with some initial state, you ran it through your unitary evolution, then you hit it with some random unitaries and averaged over the ensemble of random unitaries. But that first unitary evolution that you hit it with, that now gets replaced by this hybrid evolution, okay? And that has to remain the same at every time, because if that's not the same, then you're implicitly doing this average over measurement outcomes. And as soon as you average over measurement outcomes, this transition is lost, okay? So we really care about individual quantum trajectories. So that requires you to prepare the same state many, many times. And that's hard for reasons that go well beyond just experimental limitations on unitary control or experimental challenges of that kind. It's hard for a fundamental reason, which is that the quantum randomness of measurement outcomes, right? So there is no way to kind of force a given outcome, and this randomness of measurement outcomes requires post-selection. So if you want to prepare the same state over and over again, you have to post-select on measurement outcomes. So to, again, to make this really explicit, suppose you have, the first run of your experiment, these are your unitary gates, and those are those are the measurements that you make, and say you're measuring in the Z basis. So in the first run, you're going along, and when you sample your measurement outcomes with Born probabilities, suppose you get up, down, down for these three measurements, right? Now you do this again, and you're an awesome experimenter, and you've managed to line up your unitary so they're exactly the same as the previous run. But these measurement outcomes are still going to be randomly sampled, right? So maybe you get lucky in your second run, you get an up, you get a down, but then this third outcome will be if it's an up, then you need to discard this entire run and start over, right? Until you get the same set of outcomes. So this incurs this exponential in space-time volume overhead of post-selection. Okay, and you really just cannot get around this when you have these random measurements and unitary evolution. So how do we, what can we do, right? So so there's some things that have been proposed. Okay, so there was a nice paper last year by Mike Gullins and David Hughes, and they came up with an indirect probe of this entanglement transition that I just told you about. Okay, so they said that, okay, there's a particular protocol that you can do where you entangle a single local reference qubit at time 0, and then you run your evolution and you measure some things about this reference probe, and this ends up giving you this an indirect probe of this transition, which gives you a sort of local order parameter. Okay, so this was interesting because it gives you some way around, at least some way to detect this transition. The other thing that's been done a lot is, if you're doing kind of Clifford circuits, so if you're looking at gates that are drawn from the Clifford ensemble, then you can do kind of this kind of very simple error correction, where if you get the wrong outcome, you can immediately just correct for it with no exponential overhead. Okay, so when you're doing Clifford circuits, it's easy to get the desired outcomes that you want. But we do want to have more direct access to the dynamics of entanglement, right? So how do we do that? Okay, so in this talk, I won't be giving you a specific example, experimental protocol, but what I will be saying is a new way to realize output states of a broad class of hybrid circuits. And these hybrid circuits are those that will be space-time duals of unitary circuits. I'll explain what that means in a minute, okay? So this is not the most general unitary measurement protocol you can come up with, but it is a very, very broad class. And within this class of circuits, you can actually get these hybrid dynamics while avoiding this post-selection problem entirely, okay? And what we can show is that a protocol for direct measurement of the purity or entanglement entropy of arbitrary subsystems ends up looking like a weird correlation function in a unitary evolution that you can do, okay? So that's the goal, so let's dig into it. So what do I mean by space-time duality, right? So it's very simple. So if you have a single unitary gate, right, with two inputs and two outputs, that's space and that's time, right? So if I'm reading the circuit from bottom to top, the gate is unitary, but I can now flip it, right, and read the gate from left to right. Okay, so then these are my inputs and those are my outputs. Okay, and this gives me a different gate, and this different gate is generically going to be non-unitary. Okay, so here's a very simple example. The simplest unitary gate you can think of is the identity. Okay, so this is the identity. It just, and in terms of word lines, you just have these two word lines going that way. Um, if you do this, this just corresponds, this flipping just corresponds to a permutation of the entries. If you do this permutation, you end up getting this rank one matrix. And this actually just looks like a projector onto this bell pair state. Okay, so that's what the identity maps to. You end up reading the circuit this way. But notice, and this is the crucial point, that you're projecting onto a specific bell pair state. Okay, so this is a forced measurement. There is no longer, it's a non-unitary element, but it corresponds to a forced measurement outcome. There's no longer a randomness and choice of outcomes, right? So for instance, if you were measuring in this basis of bell pair states and you were doing random measurements, maybe you could have measured the plus cat or the minus cat, okay? But when you're looking at it in this flip direction, you're always going to measure the plus cat, okay? And this forced measurement is what gets around this fundamental issue of randomness of measurement outcomes, okay? So the point is that, these dualized gates generally need not be unitary. This particular example where you have a unitary, where your unitary is the identity, tells you that your flipped gate is actually a projective measurement onto the belt state. But more generally, it's a two-line calculation. You can show that more generally what you'll be doing is a weak measurement, and that's fine because a lot of these results for hybrid circuits carry over to circuits with weak measurements. So more generally, these flip gates will enact weak measurements. But the key point is that they always enact force measurements. So it's always the same outcome. And this is this is the key ingredient that gets around this problem. Okay. So this notion of space-time duality has been used quite a bit, and there's various recent applications of this. There's this broad class of circuits that you may have heard about, these dual unitary circuits that were introduced in Tomasz Prozen's group. And these are really cool. These are circuits that are unitary in both the space-like and time-like directions. And in this class of dual unitary circuits, you can actually do various interesting things like compute the spectral form factor exactly, actually derive quantum chaos. You have analytic control over correlations, out-of-time ordered correlators. So this is a class of solvable models which have taught us a lot about exact proofs for many of these questions in quantum dynamics. There's a similar idea. It's different in various details, but a similar idea of kind of flipping these circuits was recently also looked at by Aram Harrow, Fernando Brandao. And it was used to think about the complexity of simulating circuits in shallow 2D circuits. Okay, so this idea of kind of flipping gates and trying to understand various things has applicability well beyond what I'll just be telling you about. Okay. So for simplicity, let me focus on purification dynamics. Okay, so as I told you, we can think of pure state entanglement dynamics or purification dynamics. For purification dynamics, you have a fully mixed state, and the easiest one is just the identity. Okay, so that's your input. That's depicted with these gray lines here. You feed it into some circuit, which is in general a mixture of unitary and non-unitary components. Your output state is just M rho M dagger, right? So of course, if M was purely unitary, you just get back the identity. Nothing special would happen. So this is the output state, right? M rho M dagger that we want to measure. And if you want to measure the purity of this output state, right, which is related to the second Rayleigh entropy, then the purity is just you have two copies of this output state and you trace them over. Okay, so this is just the diagrammatic representation of the purity. So Now, so this was row out, that's the purity. Now let me just kind of view, just flip this and view it in this direction. Okay, so when I was doing my non-unitary evolution, I was feeding in this identity, and this box was non-unitary, right? This is the same diagram, just viewed horizontally. And what we're going to consider is if the non-unitary evolution, right, if M was the space-time dual of a unitary evolution, okay, so that when I view the circuit in this direction, U is unitary, okay, then what happens is that this diagram, which represents the purity for this hybrid evolution, actually ends up getting mapped to a weird correlation function that I'll describe in some detail right now in this unitary circuit, okay? So this is basically, you have a unitary UM, this is UM star, R is a reflection. So these are all just, each of these blue and red boxes is a unitary that you can prepare with perfect control, okay? These gray lines are the identities, and this is again just a trace identity operation, okay? So, all right, so what are we doing? Actually, because these guys are unitary, okay, you can show, so this looks complicated, but the pieces are very simple. Because these gray lines are identity, you can show that, the U meets the U dagger, and everything, the only non-unitary piece in this diagram is happening in the central bonds right here, okay? So those are these flipped identities, okay? So flipped identities, as I said earlier, become these forced Bell measurements, okay? So you have unitary gates on the left, you have unitary gates on the right, and you have this sequence of forced Bell measurements in the middle, okay? And since you're feeding in the identity, if you didn't have this sequence of forced Bell measurements in the middle, everything would just, you just get back there, nothing would happen, right? So you get this kind of light cone, because everything that's outside the light cone of these forced Bell measurements just gets elided to the identity, okay? So basically everything, so the way to view this in the unitary direction is that you're preparing these perfectly mixed qubits, okay? So you're initializing your qubits in this fully mixed infinite temperature state, except in the central bond where you initialize your qubits in the Bell state, okay? Then as your time evolution goes on, you act with unitary gates, and at every time step you make this Bell measurement, okay? So that represents a Bell measurement. And then at the end, you have a Bell measurement on the central bond, and everything else is just traced out and discarded. Okay, so this is the unitary protocol. Okay, that you have a sequence of Bell measurements on the center and unitary gates everywhere else. Now, so that's the initialization. So now the specific protocol is that every time, so you keep making these Bell measurements, right? And every time you make a Bell measurement, if it gives you the wrong outcome, right, which is that if you get a 0, you stop and you record a failure. And if it gives you the right outcome, which is you get back the Bell measurement, then you record a success. Okay. And we can run this protocol, several times. The number of successful runs is denoted by n plus. Okay. And what we end up finding is that this purification of these dual qubits, right? These L twiddle dual qubits evolved for this specific time. This purification for the hybrid dynamics is actually exactly equal to the ratio of successful runs to the ratio of total number of runs. Okay, so this is the unitary protocol you follow, and you can map this purity for the hybrid circuit to this ratio of failure to success. Okay, and you might be wondering here, like, I wanted to get around this issue of post selection, right? And you have to do post selection if you get a failure. So, but I'm still talking about failures here. So, so why does that? So how did I get around it? And the point is that when you're looking at this ratio, all runs contribute to the entropy you're trying to measure. Okay, so you're not discarding the failed runs. The failed runs are entering in this denominator, which is n total, and the successes are entering in the numerator. Okay, so each failed run is actually giving you information. That's not a discarded run. So that's why this does get around the problem of post-selection. Okay, so just a few more comments, which is Actually, since you're constantly making this Bell measurement, okay, the probability of success after time t means that at every time step you made a Bell measurement, okay? So if you have scrambling in your circuit, which you will in most circuits in the unitary direction, then if you started with some Bell state at the central bond, this is going to scramble away, right? And the probability that you'd get back a Bell state if you made a measurement and then you did it over and over and over again is going to be exponentially small for scrambling circuits. So actually, for most circuits here, we expect to get a mixed phase, okay, because you expect that this purity is going to be e to the minus t over tau, and it's this decay constant which gives you the entropy density, because the purity is the exponential of the second Rayleigh entropy, right? So you can use the purity to measure the entropy. You can use this decay constant of this weird correlation function to measure the entropy density. Okay, so just a few more comments. When we're doing this protocol, this is the unitary direction in time, but I want to view it as hybrid evolution from left to right, right? So if you start this way and you're doing hybrid evolution, your state is never prepared in space, right? It's prepared on this temporal slice of the circuit, but actually it's very easy to just then run some, you have a small overhead to have some ancilla qubits and some swap gates to then actually get the output state that you're interested in your lab on a space-like slice. Because in the lab you can't access this time-like slice, but you can do this very simple protocol to then get it on a space-like slice. Okay. So again, these comments, I already told you that this is not using post-selection because each failed run contributes to N total and provides key information. This does impose a constraint on what types of models I can implement, right? Because the hybrid evolutions that I'm enacting are duals to unitary evolutions. But this is, of course, still a huge class of hybrid evolutions that we can consider, right? It's as big as the class of unitary circuits, and that's a huge class. And one of the things that we're thinking actively about is, if you're thinking of unitary circuits and Cloquet circuits, unitary evolutions, you can get all types of interesting phases in the unitary direction. So what do those phases, what signatures do they have when you look at it in the flipped hybrid direction, right? Like it should show up in something in this flip direction as well. And the another caveat is that the time for which you evolve in this hybrid direction is actually related to the number of qubits you have in the hybrid direction. So there's this constraint because of this light cone that you end up getting. So you can't probe purification dynamics for arbitrarily late times, right? So if you wanted to look for hybrid evolutions for times that were exponential in the system size, you wouldn't be able to do that. But you can go to times that scale polynomially in the system size. And that's already enough to give you a lot of interesting information about the properties of this quantum error correcting code, for instance. Okay. So am I out of time? I have like one section that I can skip. So
3 minutes.
Sorry, 3 minutes?
3 minutes, including questions.
Okay, 3 minutes and questions. Okay, all right. Okay, so this is of course very general, but let me give you a very simple example of this kind of dynamic. So you have kind of you have a unitary Clifford circuit with different parameters. You have an effective measurement rate. So this is in the unitary direction. If you have identities in the flip direction, they look like forced measurements. Okay, and then we can so that's this rate P. And in addition to that, we can have these random Clifford gates. The Clifford is not necessary, but these are dual unitary gates, swaps and I-swaps. So whether you look at them in the space-time direction or time-like direction, they're going to be unitary in both directions. Okay, so P is tuning the measurement rate in the dual circuit, because when you look at the dualized circuit, the swaps and I-swaps continue to be swaps and I-swaps, but the identity ends up looking like a forced measurement. Okay, so the hybrid circuit is a circuit with swaps and I-swaps and forced measurements. And this parameter J is tuning the interaction rate, because when J is 0, you just have the non-interacting swap circuit. Again, not important. Okay, so now if you run this dynamics, you get this purification phase diagram, and actually it's interesting that you don't get, you actually end up not getting the small change of going from random measurements to force measurements means that you end up not getting you end up not having an area law phase, okay, except at this very fine-tuned parameter line. So this is related to this comment on scrambling. So generically, you end up having mixed phases, okay, except on a fine-tuned line where you're always making measurements, right? And if you make your circuit non-interacting, then you actually get an entire critical line. And this critical line you can understand in terms of this of random walk dynamics, but let me not get into that. The key point is that you end up along this critical line. You have a purity that actually goes as e to the minus square root of t rather than e to the minus t as for a mixed phase. Okay, so to summarize, space-time duality enables forced measurements and sidesteps this issue of post-selection. So this gives us a new route to investigate this broad class of hybrid circuits. Both the global and subsystem purity are directly measurable. So this allows us to study properties like the quantum code properties of this mixed phase. This gives us interesting constraints on the entanglement dynamics because the class of circuits you're considering is forced to be unitary in the transverse direction, right? So this is related to what I was saying earlier, that the unitary models can have interesting phases. So you can ask about what does that mean in this transverse direction. We've been thinking about what you can map this to stat-mech models, think of higher dimensions, think of entanglement dynamics more generally under these hybrid evolutions. So that's the big program for where we're headed. And just before we end, I would also like to briefly advertise this other work that we completed earlier last year that just got accepted into PRX. And this has to do with entanglement dynamics in measurement-only models. Okay, and this is a class of dynamics where there are no unitaries. You just have different ensembles of measurement operators, and you get this qualitatively new type of entanglement transition, which is driven by the frustration of measurement ensembles. Okay, and this allows us to look at various things by studying frustration graphs. But a key result in that paper was also a new measure for information spreading or light cones for non-unitary circuits. So usually, if you make measurements, you get this very non-local, action at a distance. But nevertheless, despite that, we can get a statistical light cone with a finite entanglement speed. Okay, and we discussed how to define that. Okay, so I will end there.
Thank you, Vedika. A few quick questions.
So, Vedika, I have a question, maybe comment or question. So, the reason you get basically generically you get mixed phase or a mixed phase is because you in 1D you need you always get scrambling in a 1D circuit. But suppose you take a 2D circuit, then in this mapping to stat-mech, you get an effective ferromagnetic model, which means scrambling and also means eventually scrambling, but you, as a function of the width of the circuit or depth of the circuit, you can have like a finite temperature phase transition of the ferromagnet. So I wonder if you also would have non-post-selected measurement that would detect this kind of transition in the 2D circuit.
Yeah, no, that's a great question. And, we've been thinking about Aram's paper more and trying to understand that. So indeed, I think in 2D, it is possible. It may be possible. I don't know the answer. It may be possible to get a transition even with these force measurements. One comment, though, in relation to what you said is that, so in 1D, you're saying that as a function of the depth is something like an effective temperature, and you should only get a transition.
Yeah, only at zero temperature, you'd get a truly ferromagnetic phase, basically.
Right, but here our circuit depth is extensive, right? Because we do have time which scales as system size. So that's the one caveat that, we do have an extensive circuit depth, but we still seem to be unable. So, in principle, you could be at zero temperature, but we still seem to be unable to get an area law phase.
I
So,
see.
so it seems to be more subtle than just that one point. But I think it's definitely very interesting to think about what the effect of StatMech model is and whether that can that can clearly show that you can't have a transition.
You're saying in the light cone dynamics, you're forced to have basically the same depth as you have the width.
Exactly. Yeah. So you are you are effectively at zero temperature. So you should be able to, in principle, get a transition.
I have a question.
Yeah.
So like just to make sure I understood. So if you don't start from a mixed state but start from the pure state in the dual picture, your measurement outcomes are always deterministic.
Yeah. So good. So this is something I skipped over, right? So I have what I didn't draw what this looks like here, right? Like there's I just drew flat vertical lines, but there's actually like boundary conditions here as well, right? So it depends on it just ends up, so if you start, instead of starting from a mixed state here, if you end up starting from a pure state, what ends up happening is that you have one level of post selection. So you'll end up with so suppose you start with all Bell states, then at the end you end up with you need to end up projecting on your Bell state. So that's if you have just pure open boundary conditions. These pictures represent depolarizing boundary conditions. And if you start from some generic pure state, that ends up looking like a specific boundary condition on this edge. So the short answer to your question is you can do all of this even for pure states. You just end up with slightly funkier boundary conditions. But we've done simulations with all of these different boundary conditions, and the presence or absence of phases and the properties of the phases are not affected by the boundary conditions, but how measurable they are in a lab setting could be affected by that.
Sorry, like my question was very naive. Like even talking about boundary conditions, I was double checking that the measurement outcomes are deterministic. Is it under certain conditions?
Yes.
Yeah, because
what's happening here is always deterministic.
Yeah, because that explains already. That statement already explains why you have a phase transition only at p = 1. The reason being, if the measurement outcome is deterministic, that means there's no entropy associated with it. And that means the environment is revealing zero information about the quantum state. And that implies that there's a certain unit, the underlying quantum system is evolving under pure unitary without any measurement. Therefore, the fact that you have a deterministic measurement all the time, if you start from the pure state, that means your underlying circuit is always unitary. Therefore, you cannot have a phase transition.
Well, okay, so this I'm not sure about, because something that we did do is, and Matteo, you can correct me if I'm wrong. So we did do just pure. There's a difference between, I think, just deterministic and deterministic that's derived as a hybrid, as a flipped of a unitary. Because I think we tried doing just the usual unitary projective dynamics of Leach and Fisher, and instead of making the measurements random, I think we picked forced outcomes with random probabilities. And there you still got a transition. Isn't that right, Matteo?
Yeah, I mean, there is a discussion in Adam Nahum's paper most recently on these transitions in models with forced measurements. That's not the key.
So it's not just that it's forced; it's the fact that it's coming as a dual of this unitary evolution. Because I think if you just do the forced measurement alone,
forcing the measurement,
you still get it.
The forcing the measurement is okay, but I'm asking about before forcing the measurement, estimate the entropy associated with the measurements. And if this entropy is 0, then means you are not revealing any information. Like before even talking about forcing it or not. In other words, if the entropy is 0, you're not really forcing it because your measurement is deterministic anyway.
Right. No, but I'm saying you can do the same kind of Leach and Fisher dynamics with perfectly deterministic measurements. So zero entropy of measurements, you'll always get the same measurement outcome. And you still end up with a transition there.
If the measurement outcome is it's not probabilistic.
Exactly. So if you replace your projective measurements with just, on every site, you go back to this first circuit and replace this with projector onto up, down, up, just a specific sequence, and you do that at every time, you still get a transition there. So it's not just a feature of the forcing.
I see. But isn't that then percolation transition, just talking about the connectivity? Because underlying circuit has to be unitary in that case. So the only way to have a phase transition is percolation type.
Well, the entropy of the state does change, right? It purifies partially and then settles on some entropy density between 0 and 1 in the mixed phase. So I'm not...
The entropy, the entanglement entropy or the entropy of the measurement?
No, the entropy density of the mixed state you're
entropy density of the steady state. Like you still get exactly.
Sorry, I was talking about the entropy of the measurement outcome. So whether the measurement is deterministic or not.
No, I know. But even with perfectly deterministic measurement outcomes, you still get this whole range of entropy densities for your steady state.
Entanglement entropy density.
This is a great discussion, and I would love for it to sort of get like hunted to the very end, like actually figure out what you guys are disagreeing about. But let me suggest that maybe we could follow this up in the Gather Town at the end of the session, or in the discussion session in the afternoon.
Sure.
If you guys can all make it, that would be really great. I would really like to continue that, but we do have to move on to the next speaker, I'm afraid.
Okay. Yeah.
So let's thank Vedika again, and let's move on to our next speaker.